Alright, welcome back. So here we are, now we're in searching. Only got one more left after this, and that'll be sorting. Now for searching, we've got about half a dozen different algorithms that we're going to talk about. Most of them are things you're not going to want to deal with. Because what it all boils down to is with a given data set, if it's a really big data set, which one do I want to use, and how am I going to choose the algorithm with a given data set? Well, it depends on what's in the data set. It depends on the structure that I'm using, but with what we're dealing with so far, it's all linear. We've got an array or a list that we're transversing to go through and find a specific piece of data. It's almost like we had a train with I don't know how many cars, n number of cars in this train, and we need to find the one boxcar that has a specific item in it that we're looking for. We don't know which one it's in, so we've got to go figure it out. And we've got 6 different algorithms we can use to go find that boxcar that has what we're looking for in it. And that's, in a nutshell, what we're going to do. So if each index is a different boxcar on our train, we've got to go figure out which one. If we were looking for the number 99, we got to find it. How do we find 99? Well, we could do a linear search. Linear means in a line, one after the other. And if this is the array that we're going to transverse, that we're going to go through item by item to go find it, linear means one right after the other. All right, let's go looking for 99. Is it there? No. How about there? No. How about there? Nope. How about that one? Nope. Up, there we go. We found it. That's it. That's a linear search. What's the worst case scenario? How long is it going to take us? How many tasks will we have to go through before we find what we're looking for? If we're looking at an array with a length of n, it's going to take us, worst case scenario, n to find what we're looking for, because it may be all the way at the end. And we can't just jump to the end and say, I found it. We've got to start at the beginning and go item by item by item by item all the way to the end. So a linear search, it's not pretty. We start at the beginning and we work our way to the end. It's for a linear, non-sorted data structure. Okay. So there's our linear search, unordered. We just pop our way through it. Like I said, worst case scenario, big O of n. Let's go look at something else. Let's say we've got an ordered linear search. All right. We start here and we work our way through. It's still a linear search. We go one after the other. So we're still n. When we're linear, it doesn't matter. With the algorithm that we're using, this linear search, it doesn't matter. Now, I could say, all right, what's the value? And what's at the end? What's at the beginning? Where should I start? From the end or the beginning? If I'm going to go linear, let me start. If the number's closer, well, ordered, if it's closer, I want to start at the other end and work my way back because it's a really high number. that linear search could be more efficient. But we're saying complexity O to the n. Now we've got a concept called jump search, and I just scratch my head every time that I go through this. But a jump search is better than linear search. We're dealing with ordered or a sorted list of elements. So things are in a certain order. And we're going to technically jump in. Now, with this, they're saying jump in. What do you mean jump? Well, we have an idea of how big our array is. It's n. Say, all right, well, n, let's break it into blocks of 3. So every 3 items will be a block. So here's block 1, block 2, block 3, block 4. And what I'm going to do is I'm going to go look at block 1, and I'm going to look at the first item, and I'm going to look at the last item. So all right, block 1, I jump to the last item, and I say, is that higher or lower than what I'm looking for? It's lower. All right, jump to the end of the next block. Is it in there? No. Jump to the end of the next block. Is it less than that? Or is it that? Yes. Boom. Then we don't have to search so much. Now this, it's more efficient than that linear search. Even a linear ordered search, it's more efficient. Because we're breaking it down. It's a divide and conquer in a way. We're breaking it up into blocks that we determine what the size is. And depending on the size of the blocks will dictate how bad things are going to get. So that's another option. That's our jump search. So that one's going off of square root of n. So that's big O, complexity would be square root of n. Binary search, that's our divide and conquer. So a binary search, time complexity, worst case, is log of n, which is the square root of n. Linear search was n. So we're doing considerably better with binary search than with the linear search. So with binary search, here's the example, but I'm gonna walk through, give you an example. So you may have written code to interact with a system to have a user guess a number. So we'll create a game where the computer randomly generates a number and then we have to guess the number. Students create a program for that in just about every semester. It's an easy program to do. Now, if we apply divide and conquer logic to this, we can guess the answer by using divide and conquer, and we end up with, if I said from 0 to 60, I can guess that number in less than 8 guesses. What are you talking about? What do you mean less than 8 guesses? Worst case scenario is going to be less than 8 guesses. From 0 to 60, you can guess it then? Yeah, absolutely. So let's look at this structure. We say this is from 0 to 60. Let's say that 47 was our number. 0 to 60, I go halfway, which is 30. I cut it in the middle. And I say, is your number 30? No, you're too low. Okay. So I've got to go between 30 and 60. Go 45. Is your number 45? No, you're too low. Okay. Now I jump in half again. And now I'm at 52. So now, how many guesses have we done so far? This is my third guess. 52. And they say, nope, you're too high. Oh. So now I'm between 52 and 45. I cut that in half. I say 48. That's my fourth guess, 48. You say, nope, you're too high. Yeah. So now I'm between 45 and 48. If I said 46, you're too low. Then I know it's 47. So I had 6 guesses. It wasn't that bad. But I knew I could get it in less than 8. Because of the math associated with a divide and conquer. So that's the logic on this divide and conquer, or our binary search. Cut it in half, cut it in half, cut it in half. Now, straightforward coding for it, and it's one of our most commonly used because of the efficiency associated with it. It only works if the data is ordered. We've got the criteria. So if you didn't have an ordered list, then you have the work set out ahead of you that you've got to go through and get this in some kind of order. All right. So that would be our sorting algorithms. That's the next lesson after this one. All right. But for just the searching part, if I've got it sorted already, I'm golden. Now, interpolation, this one's different in that we've got a formula that we're going to go by. And essentially what this means is we're going to have we're going to guess. We're not saying, hey, we're going to go in the middle. We're going to do a guess between the value at one end and the value at the other end. And we're going to plug those values in. Say, well, what's at the end? And what's at the beginning? And then we're going to go through and we're going to do some math, and that'll tell us what index to go jump to in the middle. And it may not be what we're looking for. It may not have been, it may not be the midpoint. So with that said, this one's, it's wonky. It's not an efficient algorithm. You just take the values and start at one end, start at the other, plug those values into the formula, and then that'll tell you where you're going to slice this up. It's still divide and conquer, but you're using that function rather than just cutting it in half. Okay. We've got exponential, which essentially we're going through and we're searching. It's similar to the breaking it up into groups, but instead of breaking it up into groups, we're just jumping ahead so far based on the formula, the exponential formula, how it goes forward. So we'll get to here, we get to here, then we get to here, then we get to here. So we're doing the squared. So we start out at 0, then we go to 1, then we go to 2, then we go to 4. 4 squared is 8. 8 squared, so we're actually going, using that as, so 2 to the 0, 2 to the 1, 2 to the 2. Moves us up to where we're going next. Okay. So that's another way to, let's go see where we're at. And if we do that with an ordered list, the further we go, we don't have so much to slice up, but we've got these jumps, jumps, jumps. It's not a super efficient algorithm, but it's different. Best case complexity could be constant, O to the 1, because we found what we were looking for the first time. Or this is what it turns out to be, O to the log of I, as opposed to O log n. So we've got to pick which one we want. Would you want a search algorithm with big O notation of big O n, or big O log of n? Which one would you choose? This one's more efficient. So I want to choose the most efficient algorithm that I can, right? Based on worst case scenario. Not best case, not average case. I want to go off of worst case scenario because I don't know what's going to happen. Okay, so I'm probably going to have another video along with this one. This one will be on the overview page, and then you'll also likely have something else to go along with it on the lecture page. Right? It may or may not. Just jump over there. Always jump to the lecture page to see if there's other videos to go along with it. And we've got resources for you in the Module 10 or the Lesson 10 resources page. Both should have a Colab notebook for you there, along with the publisher's resource link to their GitHub. Okay, so with that said, we'll see you over in the sorting lesson, which is our last lesson.